Hello and welcome to today's webinar where we're going to demonstrate how FEFLOW can be used to calculate pressure, heads and fluxes into dams. My name is Nilson Guiguer. I am with Water Services and Technologies, and this webinar is put in collaboration with the developer of FEFLOW, DHI, as well as with its distributor, HydroInfo. We're going to start talking about typical issues in dams. So if you have flow that puts the water table too high, you may have instability on this zone caused by the extra weight caused by the water being present in the pores, as well as the water acting as a lubricant and making it easier to slip through the slip surface in this zone here. So it can cause instability because of that. It can cause instability because you have too much flow carrying materials and causing piping over time and then causing a collapse of the structure. So in order to avoid that, one could put, for example, a drainage blanket here. So you bring the water table lower and decrease the pore pressure in this zone here. Another type of instability would be too much flow underneath the dam, which can also cause some piping and some erosion in the toe part of the dam, causing also instability in this zone. In order to avoid that, one could use, for example, a grout curtain to have a bigger energy drop between this side and this side, and avoiding the flow or decreasing the flow underneath the dam. And in fact, one can have a series of structures in a dam to avoid these and other problems. For example, one could put an impervious blanket here, so it makes longer the pathway underneath the dam. Could put some relief well, could put some rocks on the upper part of the dam, so if the water table of the water level, the reservoir goes down too fast, doesn't cause instability on the upstream part of the dam. Put some rocks here to create a toe stability berm and things like that. In tailing dams, these problems are compounded because you may have more instability on the dam itself. For example, very common practice of tailing dam is to put upstream growing tailing dams where the material comes here, then you put a new part of the dam on top of the tailing, then a new part and so on. It's the cheapest way of building a tailing dam, but also the most unstable, since the upper parts of the dam sits on top of the tailing, which may liquefy and so on. It's even more important to keep those structures active so that we don't create a huge pore pressure in the dam itself. A more stable part of it is to put the downstream construction, so the dam, the new part of the dam, is sitting on top of the existing part of the dam instead of the tailing. It's the most expensive way, but it's most stable. And an intermediate would be the center line dam, building like that. FEFLOW can calculate each one of these types. For example, the upstream design, we did this simulation for an upstream design dam with the structures here of the filters. And this is the design of the dam, and we put it into FEFLOW. And then you can calculate the different material, the filter can calculate based on the mesh, the pore pressure distribution, the water level. The same as here, which is downstream design. This is one dam that we have done downstream design with the filters and the basement, and represented in FEFLOW. Again, the grid with the filters with a smaller spacing to represent the filters, and the water table and the pressures in this case. In fact, what FEFLOW can calculate? FEFLOW can calculate both equipotential lines, so areas where each point, this point here has the same potential at this point, and so on. If the dam is isotropic, then it would have perpendicular to the potential. You have the flow lines. So FEFLOW can calculate that. And for example, the water level inside a piezometer sitting at this point here, a few centimeters of screen sitting on this point. This point is in the same potential line as this point, and here's the water table. So the elevation inside the pipe is the same as this point. So it calculates the heads up to where the water rises in the pipe from a datum. Now, so FEFLOW can calculate heads, but different than mod flow, for example, the FEFLOW formulation is not simply head. It actually considers that head is a sum of the gravitational energy given by the elevation plus the pressure energy given by pressure over rho g. And so FEFLOW can give you at any time not only the heads but also pore pressures, which is the parameter that you need to feed a geotechnical model in order to use as a parameter for the stability analysis, along with Young modules and the parameters that geotechnical use for geotechnical models. Pore pressure is one important parameter. FEFLOW also calculates flow rates, so you can know how much water to expect to collect in the filter, which you can use to design the dimensions of your filter, for example. So without further delays, let's view in practice an application example using FEFLOW of this dam that has, it's a mixed usage dam to contain tailings, and also here on top it has water that is used for water intake for the processing plant of the mine. Has the traditional items of a dam, a shoulder, a cut-off wall of a more clay material, then a drainage filter and a drainage blanket here to alleviate pressures. Has a toe drain. Here there is a downstream fill with rocks to avoid erosion at the toe here. Tailings is here. It's sitting on different types of soil, saprolite, lateritic, residual, and then it sits on a rock that can be very fractured and not so much fractured on these different layers. In order to model this system, we got the geological and geotechnical cross-section, both in PDF and DXF formats. Got soil permeability test results for each type of soil that we find. Got historical water levels within the piezometers and observation wells, and the reservoir water level and the upstream tailing depths. And then characterization and geotechnical information of all the materials. As boundary condition, we are going to use that on the upstream part of the dam. It's initially we're going to consider an average steady state solution. So it will be a constant head of 316.2. Then we're going to finalize the example by doing a transient simulation where these heads vary with time. On the downstream, we're going to use seepage phase, which basically tells the model this is open to atmosphere. If the water table wants to rise above this point, it can't. But if you want to go lower, no problem. So that's a definition of seepage phase in FEFLOW. We are also going to enter the location and the observation values for the observation wells used for calibration. And so we're going to enter a little table that has the name of the observation wells and the location and the observed water level as a constant or as a transient time series. We are also given estimates for hydraulic conductivities for each type of materials. So for example, for the tailing, we're going to enter 3.16 10 to minus 7 meters per second. For the clay cutoff wall, 1 10 to minus 9 meters per second, less permeable, and so on for every one of them. So let's start with the application in FEFLOW. So we're going to open FEFLOW, and we are going to import these polygons, which can be imported either as shape files or DXF files, and we're going to open what FEFLOW calls as super mesh, which basically has the outer polygon, and then in this case only polygons, each polygon corresponding to one particular material. Now one can also import super mesh with lines, for example, which could represent faults or rivers, or shape points, shape files with points, which could represent areas that you want to refine to represent better your wells. In this case, I only have polygons. Now, sometimes you receive the shape files and you have to do some cleanup of these shape files. In this case, for example, one can see here, these two lines almost got on top of each other. And sometimes it's common to receive a map and lines representing a river. And you have the right margin and the left margin of the river. At some point, the drawing is not as accurate, and the two lines representing the margins, they merge and they become one line. Then FEFLOW will fail when you generate the mesh. Why? Because it will try to represent a triangle basically of 0 size, and it will crash. In this case, we had to do some cleanup. These lines here, they kind of end up meeting, but the points, they're not on top of each other, the line, but it will create very small triangles here. But it will not crash because we had to do some cleanup. So we're going to generate the mesh now. So view panels meshing. And let me close this panel here. We're going to use the rate budget later. So in this mesh, you have 3 options. You have this option of advancing front, which will generate triangles, but it will not allow you to generate a bigger density of triangles in one polygon versus another. If you want to be able to have smaller triangles in one area than another, you can use triangle or grid builder. Grid builder is the best in a way that it tries to generate as much as possible equilateral triangles, but it fails sometimes. So the most common way is to calculate triangle using triangles. And the one thing that we're going to change here is the number of elements. It's a trial and error. So in this case, let's say 10,000. If I don't like, I just click here, undo, and do again. So let's say 10,000. And I could, in every polygon, change this meshing density if I want. I'm going to leave every polygon the same density. So let's generate the mesh. Okay, so let's say that I'm happy with this mesh. I only have one triangle within each filter, which for finite elements, okay. We can see it respect the lines of the properties of the polygons representing the properties, generate very small triangles in that area that I show. And, but overall, let's say we are satisfied. And now we have to define what type of simulation we are doing. Are we simulating flow only, or are we simulating mass, age, or heat transfer, which FEFLOW allows you to do? No, just flow. So I'm not going to mark any of this. Do I want to do a transient simulation where things can change? Boundary conditions, or even one nice thing of FEFLOW is that you can change any property. So hydraulic conductivity, if you want to change over time, you could. And in mod flow based models, you can't. So let's say, but in this case, nothing will change. I will do steady state. And this is an XZ model, basically. It's a vertical model, it's a vertical plane. So I'm going to tell that. And in here, I want to say, do I want to calculate exactly the saturation levels and the negative pressures above the water table? And sometimes in geotechnical problems, the negative pressures are important for stability, but sometimes not. So in this case, we're not going to use the Richards equation, which is the equation needed to calculate saturations and negative pore pressure. In this case, we have to provide functions that will tell how the hydraulic conductivity changes with pressure. Because if the soil is almost dry, then basically there is no water. Every water that gets into the soil doesn't go through. So hydraulic conductivity changes with saturation, but saturation changes with pressure. The drier the soil is, the more negative pressure you have to do to make so that you extract some droplet of water. So basically hydraulic conductivity depends on pressure. So you have to provide this function, Wangen-Urte and all the functions that FEFLOW support to use Richards equation. To simplify, and most of the times we're not so interested in the unsaturated zone, we are going to use the saturated formulation. Apply. Okay. So now, first thing is I can start adding these hydraulic conductivities. So I'm going to put here conductivity, and I'm going to put units is meters per day. No, I would like to work with meters per second. FEFLOW allows you to change the units anytime. And I'm going to pick by polygons. So if I put here, select by map polygon, I can select here to represent the clay cutoff here. But you see the halo of green light here when you change, because it's not only getting these elements, but it's also getting elements that are 3 meters from the boundary of the polygons. I don't want that, so I'm going to put snap 0. And now I'm ready to say, okay, inside the clay cutoff, I'm going to put a value of 1e minus 9 meters per second. I'm going to assign 1e minus 9. Okay. Now, I would like to save that, because if I save it, next time that I want to change the value of the clay cutoff, I don't need to select a map and everything. I just double click on this selection, clay cutoff. It will select these elements for me. So now, if I have this portion here, I put a value of 1.12. Actually, let me see how much it was. And it was the tailings 3.16 E minus 7. So 3.16 E minus 7, and the shoulder 1.12 E minus 7. Okay, so I'm going to put this value here as 3.16 E minus 7, and the shoulder, I'm going to save this before I move. Store current selection, tailings, and the shoulder 1.12 E minus 7. Assign, and store current selection. Shoulder. Now, I have 10 other polygons that I have to input. So I would have to, I could select and have different colors and different materials here for all the other polygons here. In order to save some time, I just created the same model, but with all the keys saved. So as soon as it's loaded, we're going to see that it has already loaded the different hydraulic conductivities in the system, and we can start from there. And then the next thing we're going to do is to enter the hydraulic conductivity. So if we see here, we see that this is, if we see this inspection is where one in FEFLOW can see what's happening in each element. They can see tailing 3.16, this one 1E minus 9, this one 1E minus 5. I'm going to change that because this was a previous run where I was playing with the numbers and it's not equal to the original. But because we have saved it here, so I can just double click on shoulder, it highlights the shoulder, which is I want. And the original one was 1.12 E minus 7. Okay, and the rest is basically the original value. Okay, so I can already enter the boundary condition. Let me decrease this. To enter boundary conditions, then I'm going to select here in the data. I'm going to select boundary conditions. So I go here, I say boundary conditions, head. FEFLOW accepts for flow 3 types. Hydraulic head, so I inform the solution, it doesn't need to calculate, or I inform how much water is entering the system, so it has the means to calculate heads on the edges of the boundary, or I inform a formula where it can calculate how much flux is coming in or out of the system. And it has a 4th type, which is a well boundary condition, where basically inform a flux, but it's already concentrated in one node. So it's basically a pumping or extraction well, or injection or extraction well. So in this case, I'm going to calculate hydraulic head BC, not calculate, inform hydraulic head BC on this side here. So I'm going to say on these nodes along this border, we have 316.2. And see that all nodes here, actually should be all nodes. But it's only put in this one. Let me see why. Because see, this is tricky here in FEFLOW. If you have, I put the shoulder to change. This shoulder is highlighted, it's in bold. Because it's in bold, I only see what's within the shoulders. That's why I cannot see. But if I unselect it and I assign again, then it should be, let me unselect and select again. Now I can see everything. And that's tricky because in FEFLOW, one has to pay attention what's bold, because sometimes you are doing something, nothing happens, then you see, oh, this is bold, so it's only assigning to where it was bold shoulder. Now it's okay. And what we can see is these nodes have the circle, meaning those are boundary conditions equals to non-hydraulic heads. On this side of the model, we are going to assign that this is open, everything here is open to atmosphere. And open to atmosphere means that as long as the flux is leaving the system, the head becomes constant to that elevation. If there is water that comes into the system, then the head disappears, or there is no boundary condition. Basically showing that if the head wants to go higher, it keeps there. But if the head wants to go lower, it can. It's similar to you enter a hydraulic head, but you would like to add a constraint where you say there is only a certain, now min and max depend on the direction, if it's leaving or entering the system. In this case, output, it's limited by a max flow rate. So it cannot go, max flow rate would be 0, meaning that if the water wants to get in the system, which is negative, it can't. But that's a lot of work because you have to assign a hydraulic head and then assign a constraint. In order to avoid that, and because it's a very common, FEFLOW added the seepage phase, which is basically a hydraulic head, but it's constrained, that's valid only if the water is leaving the system. So I assign hydraulic head, and we see the symbol here. The symbol is, it's a constant head circle, but it has a bar on top, meaning it's limited by a maximum flow head. If it's limited also by water leaving the system, let's say it's opposite, it's only valid if the water wants to go in the system, I will have a bar below, or it could be both. It's a very nice thing of FEFLOW that you can have these constraints. So if you have a well, you could say the well is pumping this rate, but only if the head doesn't go below, let's say 5 meters of the pump level. And then it adds a very realistic constraint, because most of the time, if you do mod flow, you don't have this constraint possibility. That means that the water well will go dry if you pump more than what the system can give. Not in FEFLOW. In FEFLOW, it pumps up to the water table, or the water inside the well, water level inside the well goes to a minimum. Then stops pumping, allows the head to calculate. You constrain by a maximum. Let's say if you have also a system that turns on the pump, if it goes higher than a certain level, you put also a maximum constraint of heads, and then you have a more realistic function. So, okay, we have the boundary conditions, and I have everything we need. We have the properties, we have the boundary conditions, we can run the system. So let's do it. So let's say, let's save it as a different name here. Save as DEM AA steady state. Okay, so now I can run. And in FEFLOW, it shows that it's running, and as soon as it runs, it will show as yellow here, this part. Let me just make sure one thing. This is problem settings. This is transient, so it will take forever. By mistake, I put transient. I'm going to stop running. It will run, but it will take some time. The problem is that once you stop, it takes a while to run. So it's stop, off. So I'm just changing here to problem settings, steady state, because now it will take no time. Okay, and I can run. Save. By the way, every time step it will take some time. Now it's just run once, and then therefore the yellow thing here means it's finished. And now I can see heads. Let me take out the face here, or the little edge. Let me see heads as lines. So let's put ISO lines. Let's just change the color here, properties, change the thickness of the line a little bit, and the color to black. Apply. Okay. Now I can lock this. So if I lock it, once I click on pressure, I don't lose it. Otherwise, it will turn off the other part. Now it's locked. Pressure, if it's positive or negative, I have, let's say here, if I just see pressure. Negative pressure means that it's above the water table. I have to apply a suction to get water out. Positive is below. Now, usually for pressure, I want to see heads, but I don't want to see continuous pressure. I just want to see where pressure is zero. That means it's the water table. So we have the water table here, and I don't want to see continuous. So I have heads and the water level. Now, I can lock this as well. So I can click again to see, for example, conductivity. So we can see what's happening here. So we can see that once it goes into the clay cutoff, it loses head quite a bit, and then once it hits the drain here, then it keeps lower into the drain, and there is an exit here. Now, if I want to see how much water it's being discharged here in this zone, well, first let's see where is it being discharged. So I can draw a line of saying I want to see any water that goes here in the upstream part of the dam, where the water is going. So I can use that line to see where the water is going. And to see where the water is going, I can use these streamlines. Streamlines forward is where the water is going. If I want to see in this exit here where the water is coming from, I could say backward streamline. Let's say a forward streamline, and I want to see here traces. So let me just turn off these edges and turn on again the conductivity, which it was locked, but it disappeared. So I'm going to put, I didn't lock the conductivity. So I'm going to put conductivity here. And let me lock the conductivity. So now I can see streamlines. Streamlines forward. Okay. So I can see here, let me lock this as well. So one can see here the water coming into here, the same flow rate between these two streamlines. It's a stream tube, the same flow rate here and here, in between every two streamlines has the same flow rate. So one can see here what's happening. And if I want to see here how much water I'm missing here, I could count the stream tubes and see the difference between the values of the streamline, but the easier way would be to say, I want to see in this exit part here, so basically it comes out from here to here, how much water I'm losing in there. So I can view the rate budget panel, and I'm going to see I could see the whole domain, what's happening, everything, but I can see just on the current node selection because I want to see in a certain portion. So in this case, it's showing that it's going out of the system. That's why it's negative in red. 0.36 cubic meters a day per meter of dam in this case, because it's a 2D. So I could use that to dimension for example, the drainage, or the drain. Use this volume to design it. Now, what happens if the drain is clogged, for example? So let's see. If it gets clogged, I have the drain, and I'm going to say that this drain, hydraulic conductivity, here, hydraulic conductivity, and I'm going to select the drainage filter. Okay, I'm going to use in meters per second here. I'm going to put here 1E minus 6. Okay, I assign this. Let's run again. And one can see that the water table went high quite a bit. In this case, I clogged the whole drain. I could clog just a portion of it and start playing. Seepage phase didn't quite go out here, but it puts a huge pore pressure here. And I could see how well it's calibrated. So I can say view panels, view charts, hydraulic head history. It's a little bit hidden in FEFLOW. And then I have to click on right click and see scatter plot. And the scatter plot becomes here. Oh, what happened here is I didn't import, but we can do it quickly. I didn't import yet the heads or the calibration points. So let me stop here. And if I could import, put one by one, I could put one here, and then I would edit, and in the edit, I would say this guy here, it's called PZ1, and in PZ1, I had an observed value of 311 meters. Okay, could do one by one, and there it would be here, or I could simply import an observation well ASCII or Excel, and in this case I have this ASCII file which basically contains the information, any number of spaces, but it has the name of the observation wells, the locations, and the value. Now, if I want to use a steady state calibration, average calibration, I use this column here. And this column here means that I have a single value. If I have a time series that has varying observations with time, I use this column, which is the number of the time series. We're going to create a time series to finalize the exercise. But for now, we're going to use this value, single value here. So let's import this data file here. So I go into maps, and I'm going to say I import. I could import an ASCII file. Sorry, I could say here add maps, and I'm going to import that guy, which is in here. Okay. And now this guy that was just imported, I'm going to convert to observation points. And then it says, where is the column that has the names? What parameter is this calibration to? Hydraulic heads or pressures or concentration, if it was the case. These are observed heads. And the value, constant value, then I give the name of value observation. Do I have a time series? If I am doing a transient, I would use this column, but I'm not. So I'm going to use this one, and all the observation values are there. And now I can run again quickly. And I can see now the hydraulic head scatter plot. And now I can see that if it was everything calibrated, everything would be in this line. Now I discalibrate, it's even worse than calibration because I played before with the clogging of this filter. It brought all the water levels up, and that's why a lot of the points are above the line. I'll have to play manually by decreasing or increasing the cutoff hydraulic conductivity, the shoulder, the underneath material. I could do this by hand, trial and error, or I could use FePEST to make life easier. And we have a whole webinar on the FePEST users, and it would find the best combination of K values to be as close as possible to this 45-degree line. We're going to finalize this exercise by making one transient run. In order to make a transient run, I have to first create time series. To create a time series, I go here and I edit a time series. So what I want to do now is to create a time series to represent the change of water level. I go the first 100 days, 640,000 seconds. The first 100 days, the water level is constant in the reservoir. After 10 days, it goes up. It stays up for another 100 days. 10 days goes down, back to the level. So simple time series. I'm going to create this new time series. So I go here, edit time series. And it's already created, otherwise I would create a new one and it will be the same. Let me call it water level data, and basically water level at reservoir. Oops. And then basically I just typed this information that I said by adding new lines here and putting new values everywhere that I want. I can't do any crazy thing. I'm going to delete this. So from 0 to 100 days is one level, then it goes down for 10 days, then it stays up, and then it goes down to 110 days and stays down. Okay, so that's the time series. And I'm going to apply this to the boundary condition. So I'm going to go there, boundary condition, and select again. If I had saved the selection, upstream nodes, I don't need to assign again. I'm just clicking on the selection, but I didn't save. So I'm going to assign again, and I have to change here. Now, yes, it is transient. So the problem is transient. Okay. And I have the simulation control. So it's running 1 year. It will start with it has an adaptive time step. It starts with a small time step, and then it checks what would be if the model extrapolate between two time steps, the value, and it calculates the head. If it's more than a certain criteria, then it will keep a smaller time step. If it's within a criteria, meaning the change in time step is almost linear, it doubles the time step for the next time step, and then it keeps creating. So let's start with some time step here and make a simulation for a full year. And now I can see that the time step is changing. It's calculating the first time. And I'm going to put view charts, hydraulic head history. And now it's calculating. This green thing here shows it's calculating. The first time step, it starts to be small, but then it starts to, see, that's the first time step. It's really small, close to zero here. 0.016. Oh, but it went, it's steady state somehow. It didn't change over time. I'm going to stop and do it again. I think I didn't save properly. Problem class. Oh yeah, it's transient. What happens here is this. It's transient, yes, but I didn't assign here a time series. I left as constant. So I'm going to assign this as time series. I only have one, which that's the name, yes. Okay, and now I can run and then it will be okay. I have the varying time steps and I will have the varying heads as we should. So it will start with a small time step, but then it will start to increase the time step, and in the end, we are going to have the variation of head with time, and basically, let's wait until the first time step starts. It is very small. Start to increase the time step, but still small. Once it goes above 1, because it's a multiplier, then it kind of speeds up a little bit. Just one more. And up to 100 days, it will be basically the water levels will be constant, then the water level in the reservoir will go up, and we will see this curve going up. And basically what we're going to have is something like this result, where the water table at the piezometers will go up and down. And if we had transient observations, we would add in the observation wells, not as a single value, but also as a time series of what are the values observed in each well, and we can do a transient calibration, which is much more difficult usually than a steady state. So with that, we will finalize. Oh, one more thing is, once we run this, what's the usage? Well, now it's almost done. But basically what I want to show is one can, after running, one would click on pressures, for example. Let's see here. On the solution, pressure. I think it will finish in 2 steps. I'm going to click here on pressure. Yeah, one more. Okay, it finished. So now pressure, what one can do is export data. So I can export pore pressures to all nodes, for example, or if I want to export just a few, current selection, but I didn't select any. But it will be export all nodes. And then it will export, and that's saying to export to the units that you chose, okay? And it will basically export, and you could export as ASCII, shape, DBF, Excel, a lot of steps. And that can be directly imported into your geotechnical model, which requires pore pressure in every node or in every region, so it can do an interpolation. So with that, we finish, and I would like to thank you everybody for attending. And here are our contacts for water services, me, for HydroInfo here in Brazil, Rodrigo, and for Alejandro Lazarte, who is the Business Development Manager for Latin America for DHI, or everywhere else in DHI, you have the email and you have contact us at any part of the world.